Okay, welcome everyone to my continuation of what are my favorite theorems. As usually, my favorite theorems, so a very biased point of view. Well, today I would like to tell you something about my favorite diamond. Here's a diamond. So in particular, what on earth is this diamond lemma? And the diamond lemma actually originates from computer science, but well, it's widely applicable in mathematics as well, and maybe some people actually would call computer science mathematics. Doesn't matter. It's a very nice theorem. I should stop baffling. It's a very nice theorem or lemma or whatever you want to call it. It's pretty surprising and widely applicable. And probably the main point is that it's widely applicable, and some things you have seen in your mathematical life actually can, maybe they weren't proven using the diamond lemma, but they could have been proven using the diamond lemma. So the main point today will be something like I explained this diamond lemma in a combinatorial fashion, and I hope you will see that this is really widely applicable, as I said, and maybe at one point in your life you will have a problem that you can solve using the diamond lemma. But let's jump right into it, right? Starting with a game, right? We all like games, and the question is, can you win? Can I win? Can anyone win? Is there, well, we'll have a look. Is there a preferred choice, basically? So it's a very easy game. I play a game on graphs. I have a graph like this one here, right? Any graph, collection of vertices, collection of edges, anything you can imagine. This was a really bad graph, but anyway, so any graph you can imagine. Maybe you want to have it to be finite or whatever, but let's not worry about that. And I want to play a game with you, or we want to play a game together. So I don't have just the graph, I have a bit more of extra information. For each vertex of my graph, I actually pick a real number. And in practice, this means I pick an integer, of course. So like down here, for each vertex, I've chosen an integer. -3, 9, -1, -2, 2, 2, for example. And that's my graph. That's where we started. And well, we want to play a game, so there should be some move. And the move is you pick one vertex, which is negative. Okay? You don't pick positive vertices. You pick a vertex with a negative weight, which is negative. And by negative, I mean the associated weight, the associated real number is negative, right? And yeah, so let's say it's -a, whatever. It could be, so here I choose this vertex, so the -1 vertex. So a is 1 in this, in this step, right? Because I'm writing -a. Anyway, so, and well, you get a new graph by the following rule. You first just simply swap the sign of the vertex, right? So -1 goes to 1. That's an easy one. That's a little bit boring. It doesn't depend on the graph at all. So the rule that depends on the graph is you also do something to the neighbors, right? You do something to the neighbors. And what you do is you look at the weight at the neighbors and you subtract a from all of them. I'll show you more examples in a second. But that's a rule, right? So pick a vertex, and the vertex is your choice, and then the game just continues. So the rule is then just flips the sign of the vertex, and for all neighbors you subtract basically the absolute value of the vertex. And you win, right? A game would be pretty boring if you couldn't win. You would win if all vertex weights at some step will be non-negative. So kind of your goal is to turn all vertex weights, so all labels at the vertices, to positive numbers. By successively swapping signs, because you successively pick a vertex, that would be too easy. Remember that you have this rule. You kind of have to be careful what vertices are connected, because from all neighbors you would subtract something. And the questions I would like to ask is, well, okay, I don't want to ask actually the question, can you win? But rather, if you win, can I win as well? It's a slightly different question in the sense that, yeah, So it's more like thinking about a normal form. I will come back to this later. But basically, that's what it is. So I ask, so let's say you have found a sequence of moves on the graph and you win. You're very happy. And the question is, are you just very, very smart and I'm just very stupid and I have no way to win anyway? Or could I win as well? And it was more than just a good sequence of moves. Because kind of a good sequence of moves depends on the game. This game will be a very boring game in the end, as you will see. So first question, if you can win, can I win as well? And second question is, if you can win, can someone do better? So maybe you can win in 10 moves and potentially someone could have won in 9 moves. Who knows? Right? That's exactly the questions I would like to ask. Given a graph, given a weighting, this is the game, and you would like to answer those questions. So let me show you 2 examples. So it's the same graph from before. It's the same graph from before, this one here. And there are 2 possible sequences of moves. So let me just do it. Here I swap the sign. So I've chosen this vertex. This is exactly the same move as before. And at the same time, I do it in a different color. I remove 1 from this vertex. Okay, so I could have chosen another vertex. So let me see. So here I've chosen this vertex, for example. I swap the sign. And from all the neighbors, I've subtracted 2, as you can see. Okay, so I don't know which graph looks better, but let's just continue. So here, the next move is from 3 to 3, and you subtract 3 from the neighbors. Right, as you can see. The next move here, as a next move, I've chosen 1, and I've subtracted 1 from all the neighbors. Good. Now I've chosen to flip 2, and I subtract 2 from all the neighbors, and then I'm basically done. Then there's this -3 left here, but I'm not worried about the -3. And I end up with 3, 3, 2, 1, 3, 3, 2, 0, 1, 1. Okay. And this graph, okay, same graph, same game, but this player, maybe this was you and this is me, started to do it differently, right? It first swaps the -1. Then I go with a 3. The next one is I take this 3 here. The next one is I take this 1, and the next one is I take this 1. And oh, surprise, surprise, you end up with exactly the same graph. So 2 observations. First of all, you won. That's awesome. But I won as well. Okay, so also I've chosen a completely different game, right? My moves were different than yours. And not just that we both have won. We both have won in the same number of steps, and we both ended with the same graph. So with the same weighted graph. That's weird, right? So a priori, I don't see a reason why this game should have those properties. Like, okay, we start with a graph. We have this weird game. You can, well, I shouldn't call it a weird game. This nice game, and you can swap signs of certain vertices, but you can freely choose the vertex you want, right? So any vertex. And this seems to be, well, let's say you have a huge graph with many vertices and many weights. There should be zillions of ways to play this game. But it seems to be like you always end up with the same result in the same number of steps, assuming that you can win. That's weird. So let's have a look at it. And actually, that's where the diamond comes in. So this is a diamond, as you can see. And the diamond is nothing else than a directed graph in this fashion. Or similarly, you could have more edges, but basically you have a target and you have a source. So you have 2 diamonds here. And it turns out, in order to prove that what I just said is true for any graph, so if you can win, then everyone will win. And the game is extremely stupid because it doesn't depend on the strategy. No matter what you do, you will always end up with the same result after the same number of steps, which is an incredible statement. Right? No matter what you do, there is no strategy. You can play as dumb as you want. And you if you win, you play very smart and I'm very dumb. If you win, I will win as well. Same number of steps with the same end result. And the diamond lemma gives you a way to prove this. The diamond lemma is basically about those diamonds that you can see here. So let's have a look at them. So here I play the same game. This was a really bad arrow. Give it another shot. I play the same game, and I decided to. There are two moves I can do. Well, there are actually three moves I could do. So let's see. So first of all, I could start with the rightmost vertex, or I could start with the leftmost vertex. If I start with the rightmost vertex, I go to the left-hand side, which is extremely stupid notation, but anyway. If I start with the leftmost vertex, I go to the right-hand side. And then I could do the same one again. I could now do this vertex, so the orange one, and I go to here, or I could do the purple one and I go to here. And you observe that. So I basically what I did is I first did move A and then move B, or I first did move B and then I did move A. And it turns out that I get this nice diamond. So they basically have a unique associated whatever minimal element at the bottom. Okay, but what does this tell you about a huge graph in general? A priori, that doesn't seem to be clear. I just looked locally, right? Locally, what's going on. Another local thing I could do here is now I play the same game with oh, it was not orange before, it was purple before, with purple, and let's say the middle one, which is red. And I do play the same game with purple, and here's purple again, and here's red, and here is red. And I end up with the same pattern. It's just a little bit of, it's a bigger diamond, but it's still a diamond, a local diamond. And I also end up with a minimal element at the bottom. So what is this trying to say? Huh? So I don't know how you feel. I just checked two local configurations. Why on earth should this imply anything for for my general game, right? General game has a general graph, a general weighting, and I just check two local configurations. But that's exactly the point why the diamond lemma is so surprising. The diamond lemma, here you go. It basically says, okay, you have some relation on a set. You can basically draw those diagrams here. And well, there is some technical assumption that you certainly don't want infinite chains. But the point is the following. You only need to check the following. So whenever you have a covering, and the covering is exactly this green picture, you can always find a diamond that closes it up. If you can check that for any point of covering, so for any kind of ambiguity you need to resolve, you can cover it up with a diamond. You locally check that you can cover something up with a diamond. Then there exists a unique solution to the problem. So there exists a unique minimal element, and minimal in the sense that, of course, kind of the target of an arrow is smaller. So AB would mean that B is smaller than A, right? B is below A. B is below A. So yes, so you only check locally that you can have diamonds, and then you get a global solution. That's the diamond lemma. The global solution, you don't need to prove that you have a global solution which is unique and minimal. So it's really the preferable solution. A normal form, that's what people would say. It's a normal form, something that everyone gets. No matter what you do, you always end up there. That's exactly my game, right? No matter how you play my game, you will always end up with the same solution, no matter what you do. And that's really good, because then this solution is preferable over everything else. It's a normal form of the problem. And the only thing, I say it again because it's so surprising, the only thing you need to ensure is that you have those local diamonds. And that's called the diamond lemma. So sometimes Newman's diamond lemma, or Bergman's diamond lemma, depending a little bit, or just diamond lemma, whatever. And it's just some links, by the way, are in the description. So if you want to check out applications of the diamond lemma, and it's just so surprising and so simple. It basically don't have any assumptions at all. I have a binary relation on a set. Wow, it's almost nothing. And the only thing I need to check are local diamonds, and then I get a normal form, a preferable choice. And it's just really good, and it's widely applicable. I listed some here. More is in the description if you want to have a deeper look, a closer look. But yeah, I mean, I hope I made it clear that this should be a very applicable theorem. So let's have a look at an example how actually it appears in the setup of non-commutative rings, which was the one that Bergman actually considered. So his paper is awesome. It's linked in the description. I think it's from the 70s, um, and it's very readable. So here I show you how to produce normal forms, these unique elements for symmetric groups. And this is basically the symmetric group. We don't know this right now, but you can identify A, let's say, with the simple transposition 1, 2. You can identify B with the simple transposition 2, 3, and you can identify C with the remaining simple transposition 3, 4. So this is a symmetric group on 4 strands, or on swapping 4 elements. And I claim it has this presentation. Okay, and that this is true, by the way, will follow from what I'm showing on this slide. So you have green relations whenever you have. So this just means I write words in my symbols. So I could write some word A B B A C maybe. So this just means I'm allowed to write. It's a free monoid generated by those elements. I just write any word in those. So this is my alphabet ABC, and I just write any word. And I have a green relation that I can write on the words, and I have an orange relation, and I have, let's say, this purplish relation. Okay. And the only thing you need to do is, in order to have this normal form, is you would like to put an order on the elements. And my order is as follows. I just say A is better than B, and B is better than C, which means I would draw arrows from, so A is better than B, so BAB, the relation, is worse. So the expression BAB is worse than ABA, because I would like to see more A's. Similarly, the CBC is not as nice as BCB. And choose some random order. So let's say AC is better than CA. And I also want to prefer short words over long words. And the question would be, now I have this free thing, this free monoid, I just write down all the words I want. And I have those relations. My word can be of length 5 zillion. And I still claim I get a normal form for all of them, but just using those relations. And the only way, I mean, you don't want to check a word of length 5 zillion. But the diamond lemma, and that's a surprising thing, is that it tells you only need to have to look at local configurations. You need to resolve ambiguities. And an ambiguity, for example, let's have a look at the right side, would be if you have a word that is B A B A B. Then you have an ambiguity because you could apply the right. You want to replace BAB by ABA, and you could do it in two different ways. And the only thing you need to check is that these two different ways, when you do it, as I did here, they kind of give you a diamond at the end. And you just write down all possible ambiguities. Here's another one, AC, AC, because again, you could do it here or you could do it here. You write down all possible ambiguities. There are not too many in this case. Basically, all of them are on this slide. And you check that you have a local diamond, and then you're done. And this is just amazing. You're just done by checking two local diamonds or a certain number of local diamonds instead of worrying about a word of length 5 zillion. And it's just really amazing. I don't know how you feel. I think it's amazing. Yeah. So let me wrap up. So you have this diamond lemma. And it's basically a lemma about rewriting things. It also appears in rewriting theory. So you have something that you would like to rewrite in some preferable normal form. Like in my game, my preferable normal form was the win situation where everything is positive. And you wonder whether this exists and whether this is unique. And in general, just it seems to be a very hard problem, but because I'm just asking a very general question. But it turns out that there's this nice diamond lemma, which says you only need to look at local configurations. And whenever those local configurations fit into a diamond picture, right? The diamond, always keep the diamond in mind, then you're good, right? So if everything fits into a local diamond, then you're good. You get a unique, you get the existence of a unique solution to your problem, whatever solution means. Yeah, so that's it for today. I hope you enjoyed the video and I hope to see you next time.